For that question, we're looking at various, calculate maximum power. Calculate maximum power that the turbine can extract from the water, okay, for this hydropower. And we got maximum power as ST, S subscript T, and it's equal to 9 times 10 to the power of 3 kilowatts. Okay? Now we have another exercise based on the pump and system head. So this is a case of two, you can say two tanks or two big tanks or two big storage tanks, maybe from lower storage tank to a higher storage tank. So therefore, to transfer the water from lower tank to upper tank, these tanks are very big. You need a pump, of course. Okay? So let's just show you a video on a situation like this. Hopefully it works. Okay, it is possible. So if you look at it carefully, you see that you can recognize this actually is a turbine in reverse operation. Okay, at night, you see that at night, the turbine becomes a pump. Okay? Become a pump, it requires energy. So it takes the energy from the electrical grid to pump, to rotate it, and it pumps the water from the lower, in this case, lower river to the reservoir or upper river. Why people do that? Daytime it is a turbine. Daytime it goes reverse. Okay? So you go reverse direction and you produce electricity. Nighttime, you use electricity that you produce in the daytime, part of it, to turn this into a pump, to pump the water back. Why do that? What do you think? This is actually happened. Eh? Why do that? What do you think? So a turbine depends on where the energy, where the rotation of the rotor, it can be a pump. Turbine in the day, pump in the night. Anybody can answer why? Why do this? The answer is very simple. It makes business sense. In the daytime, factories are working, offices working, everybody in the office towns are alive, cooking, restaurants working, people hungry to eat. So you need a lot of electrical energy, so power. So because it's a peak requirement, so you can sell your electricity at a higher price. Right? Demand supply, demand high, supply is more or less there, so the price will go up. But nighttime, factories are closed, restaurants, after 10 p.m. closed, so the consumption of electricity is at a minimum. So the price of electricity will go down at night. Daytime price will be high, at night, in some countries, electricity, the price of electricity at night is low. So therefore, you use electricity, the cheap electricity to actually convert it to a pump to pump it up there. So you sell high and you buy low, sell high like share, sell high, buy low. That's how businessmen make money. So that's smart thinking. Of course, Singapore, we don't have this variation because whatever reason, by the other countries, that's been used. So now it's turbine, daytime, the turbine. Okay, very interesting, eh? Alright. So there's a practical application. Let me just shrink this down. Let's put it back here. This PowerPoint is not that user-friendly as PowerPoint. Hope you improve. Okay, let's look at this example here. You have water is pumped from lower lake to the upper lake. Okay? With a volumetric rate of 0.05 meter cube per second. If the power of the pump is 7.5 kilowatt, the pump is 7.5 kilowatt. Determine the head and the power loss of the pump. Determine the head and the power loss of the pump. So, how do we go about doing that? Okay, so so level 1 or point 1 is 10 meter below level 2 or point 2. So we are given the volumetric flow rate, we are given the pump power, what is the head and the power loss of the pump. Because when you pump anything along a pipe, okay, there is bound to be energy required to overcome viscous friction. And this manifests itself in the form of a head loss. Head loss. Okay? So, therefore, what is this head and what is the power? Okay? Loss of the pump. So, how do we start in this case? Of course, we got to start with typical equation, that's the Bernoulli's equation. Okay, so we start Bernoulli's equation, we have T1 over gamma is the specific weight, plus okay, plus V1 squared over 2G plus Z1. Any more? No more, huh? Is equal to P2, P is small letter, small, P2 over gamma, the same gamma because it's water, plus V2 squared over 2G plus Z2 plus any more? Plus heat loss, any more? Minus the H pump. Okay, very good. Alright. So we can call this equation 1, if you like. Equation 1. So now, next, what are the terms that you can cancel off? What are the terms that you can cancel off? Okay, let this be interactive. What is P1? And what is P2? They are atmospheric pressure. Okay, so they actually gauge pressure basically. So this will cancel, this also cancel. In fact, gauge pressure is considered as 0. Okay, gauge pressure is considered as 0. Hold on, Z1. Z1 0. Okay, Z1 you cancel 0. Z2 is 10, huh? Z2 is 10. Okay. So Z2 is 10 meter. What about V1? V1, V2, because they actually very big surface, very big lakes, reservoir or river, very big surface. So the change in height, you cannot see. The change in height with respect to time is very, very slow. You know, water level go down, here go down slowly, here go up slowly. So as good as 0. Okay? The change in the water height is as good as 0. So 0, 0. Okay? Okay. So, and what is gamma? Gamma is given as, we just said gamma, 9.8 okay, kilonewton per meter cube. Okay. So, Therefore, from equation 1, we have got heat loss is equal to heat of the pump minus Z2 tank, Z2 tank. Okay? And let's call this equation 2, if you like. Now, we have got one equation there, equation 2, HL versus HP. We need to find HL, okay, we need to find Q, but what is HP? HP gets in the way. How do we find another expression for HP, involving HP? Pump head. We are given what? We are given the pump, power of the pump is 7.5. Okay, so we know that pump head denoted as the cos HP is equal to pump power, okay, pump power over Q times gamma. Okay, we learned this before. So what is the pump power given to us? Is 7.5 times 10 to the power 3 watts over Q. The flow rate is 0.05 meter cube. So Q is 0.05. Okay? And what is gamma is 9.8 times 10 to the power 3. So therefore, we have got HP is 15.3 meter. That's the head of the pump. Okay? 15.3. So the pump can produce a head of 15.3 meter. 15.3 meter. But because of viscous friction, it loses some of this head in the form of HL. So therefore, from equation 2, we have HL is equals to 15.3 minus 10. So the head loss is 5.3 meter as a result of viscous friction. Okay? Then what would be the power loss in this case? What would be the power loss? Power loss would be okay. So the power loss due to this heat loss. So if there's a heat loss, there's a power loss. Okay? Power loss by the pump. So we know that it's actually Q, gamma, and what? What's the next term? It's given by master times heat loss. Okay? Always the flow rate times gamma times whatever heat. Okay? That is the power involved related to that heat. So Q is 0.05 and we've got gamma as 9.8 times 10 to the power 3 and we've got the heat loss as 5.3. Okay, so it gives you 2.5 kilowatt. Okay, so the power loss of the pump is 2.5 kilowatt because it has got to overcome the viscous friction, which gives a heat loss of 5.3 meter. Okay, so far so good? Right. Any questions? Quite clear, huh? Good. Right, so we have finished topic 8 already, major and minor head losses. Okay? So now you are given a pipe problem. You should be able to calculate power of the pump, power of the turbine, the head loss because of viscous friction, and so on and so forth. Okay, now we go to topic 9, major and minor head loss. So far, we talked about head loss.